This lab will first be to predict the behavior of circuits containing resistors in series and parallel, and then from there we will use multimeters to measure the actual values of conventional current and potential differences in the circuits, and then from there we will examine the behavior of ohmic resistors and capacitors. In this lab, we will discuss electric potential as well as current and circuits, and then from there we will also look at resistors, capacitors, and Kirchhoff's law. We show Kirchhoff's loop rule using two batteries and two resistors in series, as you can see in the graph on the left. Then we will illustrate how the current of a capacitor charging and discharging asymptotically approaches 0 amps over time in the graph in the middle. And then finally, we will illustrate the concept of time constants in RC circuits. That's electric potential, which is the change of potential energy for any charged particle moving through an electric field, as you can see in the diagram. And potential energy is equal to charge times the electric potential, and electric potential is equal to the electric field dotted with the displacement vector. Current describes a bunch of mobile charges, usually electrons, moving through a conductor, and the conventional current is in the opposite direction of the drift speed and the electron current. Circuits will discuss resistors, where resistance is the measure of the opposition of the flow of current, where resistance is equal to the resistivity times length divided by area. We also discuss capacitance, where capacitance is a measure of the amount of charge that a capacitor can hold. And we also look at Kirchhoff's laws, both the node rule and the loop rule, using the CCK. So in the CCK, you assume that both the batteries and wires have no internal resistance, and similarly, the resistors and capacitors have the exact resistance and capacitance that is listed. In this lab, we also use the model delta V equals delta V naught times E raised to the negative T over RC in order to determine the time constant. First setup for demonstrating Kirchhoff's loop rule. So the system is a circuit and the surroundings are everything else. You can see that we have two batteries, two resistors, and two ammeters in series, and you can see that if we flip the ammeters, the reading does not change. Use the setup to determine the potential drop across different sections. You'll see that delta V is equal to 3 volts, delta V2 is equal to negative 0.96 volts, V3 is equal to 0 volts, V4 is negative 2.04 volts, V5 is 0 volts, and V6 is 0 volts. We can illustrate Kirchhoff's loop rule by adding all these potential differences together and seeing that the total potential difference for the entire circuit is 0 volts. Since we know that current is constant in series, we can find the total resistance by adding R1 and R2 together from our initial conditions, as well as the total voltage by adding V1 and V2 together from our initial conditions. And then we can determine that I1 is equal to I2, which is equal to the total current. Then by applying Ohm's law, we can see that IT equals 2V over R1 plus R2. We can graph these changes, and then we'll also note that the voltmeter doesn't actually change the resistance, so the total resistance is the same, and therefore the current of the entire circuit is the same. Similarly, if we connect the 100 ohm resistor in parallel with an ammeter, the current read is undefined, as the current does not flow through the path with any resistors in it. Instead, it only flows through the ideal wire, which has a resistance of 0 ohms. Therefore, the current is given by V divided by 0, which is infinity. For this simulation, the ammeter and the wire have a resistance of 0 ohms, while the resistance of the resistors are 47 and 100 ohms, respectively. This is our setup for illustrating some principles about RC circuits. The system is still the circuit, and the surroundings are still everything else. As you can see, the light bulb is initially very bright as the capacitor begins discharging from the plates, but the current asymptotically approaches 0, beating in at I equals 9 volts divided by 10 ohms, since the capacitor behaves like an open wire at T equals 0. The capacitor immediately begins discharging at time equals 0, so the initial current was just Q divided by C over R, where Q was the amount of charge stored in the capacitor. However, as the capacitor discharges, the current asymptotically approaches 0 again. The charge time with 10 ohms was about 11.43 seconds, and the discharge time was about the same, whereas the charge time with the 20 ohm resistors was about 10.56 seconds, while the discharge time was about 10.67. Resistance and capacitance being at a predicted time constant of 6.0 farads. And then from there, we can also get the slope of this graph, that is the natural log of V over V naught versus T, to be negative 0.1668 about. Know that the slope is equal to negative 1 over RC, and so therefore we can get an actually experimentally determined RC at about 5.994 faradohms. We have successfully showed that Kirchhoff's loop rule using two batteries and two resistors in series. We also illustrated how the current of capacitor charging and discharging asymptotically approaches 0 amps over time. And then finally we calculated the time constant for a simple RC circuit to be about 5.994 ohm farads, which closely matched our predicted answer. Simulating the ideal environment, it would be significantly different from the real version. And for the time components of the lab, I was manually starting and stopping a stopwatch, which was very inaccurate. The real ammeter would have some kind of internal resistance in it, so therefore we would measure a potential drop-off as well as a smaller current than in the ideal scenario. Likewise, if we remove the resistor and just plug the real capacitor to a real battery, there would still be some kind of internal resistance in the battery, so there would be a much steeper slope in the graph, but still asymptotically approach zero.